here we go. This one is for the MIPS R Type instruction. So a quick recap to the introduction to MIPS architecture tutorial. In that tutorial we learned that there is basically 3 types of MIPS instructions, MIPS instruction formats, sorry. So MIPS instruction formats are of 3 types. The first is R type, second we have I type, and third one we have J type. Each type has its own purpose, has its own format, and we're going to be learning about all 3 and how to represent each MIPS instruction in this format just in a little while. So this was a quick recap. Hopefully you guys remember this. Okay, let's put that here. Now, beside me on this left side of the screen, you can see that we have 2 MIPS instructions. We have the add instruction with register T0, S1 and S2. Now, what this instruction basically means is that we're going to add the contents inside register S1 and along with the contents inside register S2, and we're going to store that contents inside of T0. I'm going to repeat that because I understand that could be a little confusing at first. So T0 here is basically the destination. S1 register is source 1 and S2 is source 2. Alright, so T0 is basically going to be equal to S1, the contents of S1 plus the contents of S2. Okay, so that was our add instruction. Next, we have another instruction here. This one, as you can see, I've written SLL. So what that basically means is that shift left is represented by SLL. So here your destination is again S2, register S2. In R type instructions, the first register that you see is always your destination, the leftmost one. So S2 is the destination. T3 is our source. And 2 is your the number of bits that you have to shift. So what's going to happen here is that the contents inside the register T3 is going to be shifted left twice because our shift number is 2. It's going to be shifted left by 2 bits, and the result of that is going to be stored in S2. Okay, so that's what that basically means. And both of these instructions are examples of R-type instruction. We have a lot of other examples of R-type instruction. For example, we have mult, we have nor, XOR, OR, and you'll find a ton of R-type. If you just look at the link that I've put in the description, you'll find a full reference sheet of the whole MIPS instruction architecture. Okay, so now we've learned what these instructions do. Now let's take a look at this bit here. Every MIPS R-type instruction has to be represented in this format. So we have a total of 32 bits here. So the total will be 32 bits. And these 32 bits are divided into 6 sections. So the operand, the first source register, the second source register, the destination register, the shift amount, and the function bits. So just take a look at this blue box that I've put down for you guys. The operand is 6 bits, and as a rule for R-type instruction, the operand is always equal to 6 zeros. So operand for R-type instruction is equal to 6 zeros. So whenever you're going to be representing an R type instruction, begin with the operand and begin with 6 zeros. Don't forget that. This is really, really important. So I'm marking that in red. Next, we have our first source register. So in the add instruction, as I told you guys before, the first source register is S1. So in this place of 5 bits, you're going to have to put S1 there, the value for S1. We're going to get to that in a bit. So this is the first source register and this is the second source register. The destination, as I told you guys, is either going to be T0 for the add one, and for the shift left one, it's going to be S2. The shift amount, right? So when we're going to be using instructions like shift left or shift right, shift right is SRL, by the way, so you should know that too. When we're going to be using these shift instructions, we're going to be needing the shift amount. So for this instruction, the bit representation of 2 will be put here, the binary representation of 2 in this space. But whenever we're doing something except for the shift instructions, for example add, so this place is going to be 0. So if there is no shift value, then SHAMT, which means shift amount, is equal to 5 zeros. Finally, we have the function bit here. So every instruction in the MIPS architecture, for example, the add instruction, has a specific value for their function, the function representation. So in the question, you will always be given what the add, instruction represents or what shift left represents. And your job is just going to be putting that inside the space here. So let's work on solving these ones. Let's show these two instructions in the R type format. Okay, just give me a second. Let me clear some space. We don't need this anymore, and okay, I'm just gonna leave this where it is. Take a look at this note that I just bought for you guys here. The values that we saw in the previous slide, the register file values, you will now get that why I began with that. These are the values that you're going to be needing. For example, in the huge table, okay, I'm just gonna show that to you guys again. Let's save this. Yeah, in this table, just see that T0 was equal to register 8 and S0 was equal to register 16. So this is where I got the values from. So don't be confused in that regard. Go back here. Right, so T0 is 8, S1, since S0 was register 16, S1 will of course be register 17, then S2 is 18, and T3, if you just figure it out, it's 11. And I've also included what the binary representation of the add instruction is. Now this is a fixed value and it will most probably be given to you in the questions, so don't think that you need to memorize this one. Okay, so for the binary representation of this instruction, let's get started. We're going to start off with the 6 zeros because why? Because the R type instruction always starts off with 6 zeros in the operand space. Next, we're going to represent the RS, the first source register. So for the add instruction, the first source register was S1. So what you're going to do here is represent 17 in its binary format. So that will be 1 0 0 0 1. That's the one for 17. Next we have the second source register, which is S2. Now S2 is 18, so that's going to be 1 0 0 1 0. Now this needs to be done in a single line. There, that's better. Then we have our destination register. So for the first instruction, that's T0, which is basically register 8. So 0 1 0 0 0. And since this is for the add instruction, no shift amount is here. These are going to be 5 0 bits. And finally, we have our function. So for the add instruction, the binary representation is this, and there you have it. This one is the R-type representation of the first instruction. Now for the next one, let's move on to SLL. Again, we start off with 6 zeros. Now our first source register is T3. So T3 is represented by register 11. So it's going to be 0, 1, then we're going to get 0, 1, 1. That's for 11. And then since we don't have a second source register for the shift instruction, I'm going to leave the second source register space as just zeros. That's what you can do. And I did it for the second source register just because of convention, but I don't think that if you do it for the first one, leaving this one 0 and putting the first source register here, it'll be wrong. So, but it's better to do it this way. Okay, next we have the destination register, which is S2. So that's 18, 1, 0, 0, 1, 0. Now for our shift amount. So shift amount is 2, just represented, 1, 0. And finally our function, function bits for SLL. So since I don't know the binary representation of the shift left instruction currently at the moment, I'm just going to leave these bits as 6 X's. So in the question, I'm going to repeat it again, you're going to be given what to put in this space. So since I don't know it at the moment, I'm going to leave that part as X. But you get the point, right? So this was our basic MIPS R type instruction. Let's move on to the I type one. Okay, I type MIPS. Save this, and here we go. The MIPS I type instruction. So as you can see, we have a few familiar abbreviations here. The first 6 bits are again the operand. The next 5 bits are the source register, and the next 5 bits are your destination register. And there is also a space here for the constant or the address. So I'm just going to jump right into the representation here, and you'll understand what to put in this space. So some examples of I-type instructions are the load store, which means, okay, we're gonna have to reference back to our introduction video. So load LW means loading from the memory, and SW means storing to the memory. We also have branch instructions, BEQ, BNE, and some more like ADI, and then sub ADI. There are lots more you can see in the entire register file. So there are a lot more, I-type instructions, which you'll find in the link that's included in the description part of this video. So let's get started with the load instruction. Okay, so I'm just going to assume that the operand for the load instruction is, let's say, 0, 0, 0, 1, 1, 0. This is an assumption. You guys should remember this is an assumption. Since I'm not showing you, an answer to an exact question, we're going to have to assume that the load instruction's operand is this. Next, we have our source register. So in order to understand this, at first you're going to have to understand that what is going on in this load instruction. This basically means that load the data contained inside this memory address that I'm marking here, this memory address, into the T0 register. Okay, so the 4 and then the bracket with the S3 register inside, what does this represent? It represents a significant memory address. And the contents of this memory address is going to be moved to or loaded from the memory into the T0 register. Alright then. So how will you calculate the memory address from this 4 then bracket to S3? This basically means, okay, I'm just gonna put note here. So load T0 and then we have 4S3. This means move data inside the memory address 4 into S3 into the register T0. Alright, so 4 into S3 basically means this. It's the memory address represented by 4 plus the address of S3. Okay, you're just going to have to get your head around this because I understand it can be confusing at first. Memory address of 4 plus address of S3. Alright then. Okay, so this is what the 4 and then the bracket S3 means. It's a memory address. And how do you calculate the address? 4 plus S3. Alright, so that's out of the way, and I'm glad it's out of the way. Once you've understood this, the rest of the process will become a lot clearer. Okay then, so here in this load instruction, the source is this register S3, the destination is T0, and the constant is this number here, which is 4. So you're just going to have to remember this format so that you can represent the instructions in a similar way. So our source here is S3, and we know that S0 is represented by 16, so S3 is going to be represented by 19. So our binary representation of the number 19 is 1 0 0 0, and there's a 1. Next we have our destination register, which is T0, and T0 is 8, so 0 1, then 3 zeros. And finally for our constant, right? So our constant is 4, alright? But if we represent 4, it's just going to be 1 0 0, 3 bits. But see, we have an obligation to put this as 16 bits because every single MIPS instruction has to equal to 32 bits. So we're going to do this thing here, which is called sign extending. Okay, so sign extending is just putting zeros to make up the number of bits that we need. So 0 0 0 0 4 8, then 4 8 12, and finally we have 0 1 0 0. This is what we're going to have to write to represent the number 4, which is our constant here. And this entire thing is our representation of the I-type instruction load T0 for S3. Next we have store. So what load did was it brought the contents of this memory address from the memory and loaded it into T0. Store does the exact opposite. T0 is the source here. The contents of the register T0 is going to be stored in the memory address that's written on the right. So here is our second note. In the store instruction, data is brought from register and stored to memory. Stored in memory. Okay, so our source here is T0 and destination is 8 into S3. Good, now that's out of the way. And then we can just move on to, representing it as bits. So again, I'm just going to assume the operand. You will be given this in the question. And let's just assume it's 111. So our source here is T0. So first of all, you're going to have to represent T0 here. So T0, as we discussed before, is equal to register 8. So 0, 1, 0, 0, 0. Next, we have 8 and S3. So our destination here is going to be S3. So S3 is register 19, 1, 0, 0, 0, 1. And then we have our constant, which is 8, which simplifies things for us. So 0, 1, 0, 0, 0. Okay, so that's, oh no, wait, I did leave out one thing here. So this is the representation of 8, but we're going to have to make this into 16 bits because, every instruction has to be 32 bits. So we are about 11 bits short. So 1, 2, 3, 4, 8, 9, 10, 11. So this is the total of 32 bits now, and we are good to go. Next, we have a much simpler instruction, add I. So add is an R-type instruction, but whenever you're going to introduce an immediate value, which is, the 14, any value that is not inside a register is called an immediate value. And when you're adding or doing any operation between a register and an immediate value, usually there's going to be this I, small I here. So what this means is add immediate. Here your destination is going to be T0. Your first source is going to be T1, and your constant is going to be 14. Okay, so I'm just going to start that here. Again, your operand is whatever you like it because no value has been fixed here. And then our first source, actually our only source, is T1. T1 is represented by 9. 0, 1, 0, 0, 1. That's 9. And we have our destination, which is T0, 0, 1, 0, 0, 0. And our offset value or constant value, which is equal to 14. Okay, so 14, your first few bits are going to be 0. And then we have 1, 2, 16. We have 1, and then 1, 3, 1, 0. I think this one is correct. So 2, 4, 8, 12, 13, 14. Yep, that is correct. And this entire portion is your constant here. So this entire portion represents 14. Great. Now we can move on to our fourth one, BEQ. BEQ means branch if equal to. So you're going to be learning how to use BEQ and BNE. BNE means branch if not equal to in the next tutorial, where we're going to learn how to code in the MIPS instructions. For now, you just have to know that branch if equal to is the equivalent of an if-else statement. Alright, so BEQ basically is the MIPS for if-else statements. That's all you need to know for now, and you need to know how to represent it. So branch if equal to T0 and T1 else. So this is how we're going to represent it. We're going to start off with x. X, 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 X. Next, we're going to be representing T0 as our source. So here there is actually no source and no destination. So it just compares the value in T0 and T1, and if they're equal, the code will then go on to the else, to the address represented by the else statement. Alright, so let's assume here, the else instruction or the else, let's call that variable. What's else variable? Represents address, okay, 14. Alright, so the else here, it represents address 14. So now we have our immediate. So the first 6 bits are the operand, which you're going to have already. Next, you're going to put T0 in the place of the source, and you're going to put T1 in the place of the destination. Again, I'm repeating it. BEQ has no source and no destination. It just compares these two registers, the values inside them, and if they're equal, they will jump to else. So the value for T0 is going to be represented first, and that is 01001, and then T1, which means 9. So 0 1 wait, this is 0, so 01001. And finally, since the else variable here is representing address number 14, I just assume that here we're going to have to represent 14 here. So 0 4 8 9 10 11 12, then 1 1 1 0. And there you have it. This one is for our branch if equal to instruction. You can do the same for all of the others. You can do it for branch if not equal to, and for all the, the other I type instructions in the same way. I hope this helps. Oh, an important thing you have to remember between the load and the store instructions. In the load instruction, it's from the memory to the register. So the first one on the left is the destination. In load, the first register is the destination, and in store, that is completely flipped. So in store, the first register is the source, because we're moving something from a register to a memory location. That's all you need to know for the I type instruction. Let's now move on to the J type. And thankfully, this is our last MIPS instruction format, and it's quite easier than the other two. So J loop, what does this mean? It basically means jump to the place in your code which has, the loop variable stored. So okay, I understand that would have been more helpful with a piece of code, but you'll find that in the next tutorial. So J loop means jump to the line of code that has loop. So there are two things that you need in your J type instruction. You're going to need a 6-bit operand. 6-bit operand like the other two instruction formats, and you have a 26-bit address. So let's assume that loop represents address, okay, we're just gonna go with 14 again, it's easy. So loop represents address number 14. You're going to start off with a 6-bit operand, and you're going to continue to 26 bits of representing the number 14. Okay, so let's do that here. So x6 is here to represent the operand, and 26 bits here for the for this loop. Okay, now 26, 24, this is 26, but for 14, 1, 1, and then 1, 0. Alright, so if you count it, you'll get that all of this is 26, and you just have to join it to make sure that it's all 1. Alright then, so that's done for the first instruction. Next we have the second type of jump instruction, which is called JAL. Now what's the difference between just jump and JAL? So this one means jump to loop. and this one means jump and link to loop. In procedures, when we're calling, a procedure, we usually use this JAL, instruction. So what it does is that the JAL instruction stores the address of the next instruction in the code to the register RA. Alright, so whenever you call the JAL instruction, the address of the next instruction in the code segment is going to be stored in the return register RA. So RA is the return register. And then it's going to jump. When the function has finished executing, it will return to the address stored in RA. Function will return to the address stored in RA. So this is, quite simple. JAL is called, the address of the next instruction is stored in RA, and when the function has finished executing, it will return back to the address that was stored previously in RA. So that's the only difference between J and JAL, and you can represent it in the same way as I've just shown. The difference will be, if we assume that the loop is 14 here too, just the difference will be the operand here. Alright, so this was our third type of MIPS instruction, and thank you all for listening. And we stop here.